analyzing several factors simultaneously, factorial designs. Many experiments involve the study of two or more factors, like temperature, pH, and concentration during an enzymatic reaction, the route and the hour of the day on the total time to commute from home to work, and sugar and butter amounts and oven temperature in a cookie recipe. A factorial design means that in each complete trial or replicate of the experiment, all possible combinations of the levels of the factors will be investigated. If there are A levels of factor A and B levels of factor B, each complete replicate will involve A-B treatments, and we call it a cross-factorial design. Let's take a look in this example of a two-factor factorial experiment with both factors A and B being tested at two levels each. We call these levels low and high, and we use the minus and plus signs to identify them. To make it easier, let's take the example of the effect of the route and the hour of the day on the total time to commute from home to work. In this case, factor A is the time we leave home, can be 7 a.m. or 8 a.m. Factor B is the route we take, R1 or R2. And our response is the commute time in minutes. The effect of a factor is defined as the change in the response produced by a change in the level of the factor. We call it main effect because it refers to the primary factors of interest in the experiment. In our example, the effect of factor A, the time we leave home, is the average commute time we take when we leave at 8 a.m. minus the average time when we leave at 7 a.m., 21 minutes. In the same way, the effect of the route is the average time we take when we use route 2 minus the average time when we use route 1, 11 minutes. The effects graph can easily illustrate this behavior. Here we see that leaving at 8 a.m. causes an average increase of 21 minutes in the commute time compared to 7 a.m. and using route 2 causes an average increase of 11 minutes in the commute time compared to route 1. In some experiments, we may find that the difference in the response between the levels of one factor is not the same at all levels of the other factors. In this modified example, the leaving time has a positive effect when using route 1, meaning that we take more time to go to work if we leave at 8 a.m., but the leaving time has a negative effect when using route 2, meaning that we take less time to go to work if we leave at 8 a.m. Because the effect of the leaving time depends on the route, we say that there is an interaction between them. The effect of the leaving time at route 1 is 30 minutes, and the effect of the leaving time at route 2 is minus 28 minutes. Interactions between factors can be easily spotted in graphs. In the graph on the left, the increase in the commute time by leaving at 8 a.m. is roughly the same using either route 1 or route 2. There is no interaction, and the lines showing the effect of the leaving time are approximately parallel. However, the graphs on the right tell a completely different story. In the upper graph, the leaving time has a weak or small effect when using route 1, but a strong effect when using route 2. In the lower graph, the leaving time has a positive effect when using route 1, meaning the commute time increases by leaving at 8 a.m., and has a negative effect when using route 2, meaning the commute time decreases when leaving at 8 a.m. In both cases, the effect of the leaving time on the commute depends on the route, showing a clear interaction between them. Why using factorial designs? Which are the advantages of factorial designs? Let's suppose we have an experimental space with factors A and B, and we wish to maximize the response or outcome of the system. To make it easier, let's say that our response is the yield of a chemical process with temperature and pH. Our first approach is testing one factor at a time, and our first experiment will be at 30 degrees and pH 4, and the yield was 25. Now we are going to increase the temperature to 50 degrees, and the yield was 15, Now we know that the temperature has a negative effect on the yield. So we go back to 30 degrees and test the pH. At 30 degrees and pH 6, the yield is 30, and we know that the pH has a positive effect on the yield, and this is probably our best result. What we have missed is that the system is non-linear, and there is an interaction between the temperature and the pH, as shown by the contour lines. When testing one factor at a time, we miss the information about interactions, and in this case, we have missed the area of the highest yield in our experimental space. By doing a factorial design, with only one more experiment, it is possible to increase the information on the true behavior of the system. Now we know that the temperature has a positive effect at pH 6, but the temperature has a negative effect at pH 4. And the pH has a weak effect at 30 degrees and a strong effect at 50 degrees. A factorial design is always necessary when interactions may be present in the system to avoid misleading conclusions. To optimize a system using one factor at a time, we need luck. But to optimize a system using factorial designs, we only need method. Let's take a look in this example of a two-factor factorial design. A researcher needs to design a battery to be used in extreme temperature variations. There are three choices of materials to be tested. Once the battery is in use, there is no control over the temperature the device will encounter, and it is well known that the temperature affects the effective battery life. The battery should be robust to temperature variation. The following questions must be answered. What effects the material type and temperature have on the life of the battery? And is there a choice of material that would give uniformly long life despite the temperature? The table shows the factorial design performed. This is the simplest type of cross-factorial design since it involves only two factors. Factor A tested at A levels, factor B tested at B levels. Each replicate of the experiments contains all A-B treatment combinations, and there are n replicates. In our case, the material type is factor A, tested at 3 levels each. The temperature is our factor B, also tested at 3 levels each. The number of different treatments is 9. We have 4 observations per cell, the number of replicates is 4, and the total number of observations is 36. The order that the ABN observations are taken is selected at random. This is a completely randomized design. In the same way of the one-way ANOVA, we can use the effects model to describe the experimental observations. In this case, each individual result Yijk can be described by the overall mean plus the effect of the factor A plus the effect of factor B plus the effect of the interaction AB plus a random error. The analysis of variance will test the effects of A, B, and the interaction AB. So the analysis of variance table presents the total variability of the data split into the variability of factor A, factor B, and the interaction, in our particular case, material, temperature, and the interaction between material and temperature. Each one of these sources of variation will be compared to the error by using the F-test, that is the ratio between the mean square of a factor or interaction and the mean square of the error. In this slide, we have the computing formulas for the two-factor ANOVA, but we are using Excel to calculate them. Please download the file Microsoft Excel Battery Life and verify that the Data Analysis Toolpack is already installed in your Microsoft Excel. In this Excel file, we have the data of the two-factor factorial design, evaluating the effects of the material type and the temperature on the battery life. We are analyzing it by using a two-way analysis of variance. To perform the analysis of variance, we are going to select Data and Data Analysis. In the Data Analysis window, we are selecting ANOVA two-factor with replication and click OK. Now we have to select our input range, our data. I'm going to select. We have to say how many rows we have per sample. In our case, we have 4 rows per sample of the 4 replicates. Then rows per sample is 4. And the significance level is 0.05 alpha. Now we are going to select the output range. I'm going to select only the first cell of the output range and click OK. The two-factor analysis of variance with replication shows the following results. We have the summary of each treatment with the count, the number of observations or the number of replications, the sum of all observations, the average, and the variance. This information is shown for each treatment, each combination of temperature and material. Here we have -10 on material 1, material 2, material 3, 20 degrees with material 1, 2, and 3, and 50 degrees with material 1, 2, and 3. We also have for the materials, the total of the materials, and the summary for the temperatures. Finally, the analysis of variance shows the following source of variability. Sample and columns. In our case, samples are the materials and columns are the temperature. So we are going to replace sample are the materials. And columns the temperature. The interaction between them and with him. With him is inside each treatment, means the error of our system. Let's transfer this result to the presentation to analyze it more carefully. Here we have the resulting analysis of variance table for the effects of the temperature and material on the battery life. We have the source of variation, sum of squares, the degrees of freedom, the mean squares, the F0, the critical F, and the p-value for the material, the temperature, and the interactions between them. To remember, a factor or interaction is significant if F0 is higher than the critical F, meaning that the p-value is lower than the significance level alpha, usually 0.05. Before going further, it is important to point out that the critical F is not the same for all the tests. This is because of the different degrees of freedom of each term. The analysis of variance will help us to answer the following questions. First, do the different materials affect the battery life? And the answer is yes, they do. F0 is higher than F critical and p-value is lower than 0.05. Second question, does the temperature affect the battery life? And again, the answer is yes, it does. However, we already knew it from the statement of the problem. It is well known that the temperature affects the effective battery life. The real question here is the following. Is there a choice of material that would give us uniformly long life despite the temperature? This way, the test with temperature was not to see if the temperature affected the battery life, but to see if the effect of the temperature on the battery life was different for different materials. And the answer again is yes, it is. The behavior of the battery life with temperature depends on the material. To visualize this behavior, we have the final results presented as a table with mean and standard deviation and as a plot. In the graph, it is easy to visualize that the battery life decreases with temperature for all materials, but the behavior is different for material 1 compared to materials 2 and 3. After the analysis of variance, the next step is to compare the treatment means using Tukey's test. The table already shows the final result as mean and standard deviation of the battery life for each treatment. Tukey's test compares the difference between two means to a limit value T alpha to state if they are significantly different or not. The limit value T depends on the significance level, the number of treatments, the degrees of freedom of the error, the mean square of the error, and the number of replicates. The Q value can be read in a specific table, as we have already seen. This way, our calculated t-value is 61.9. Now we are going to compare the results for each temperature to decide if the behavior of the materials differ or not. At minus 10 degrees, the battery life is similar for all materials since the difference between them is lower than 61.9. At 20 degrees, material 1 has a shorter battery life than materials 2 and 3, and at 50 degrees, again, there is no difference between the materials. It is pointless to compare the temperature within the materials, since we have no control over it. We cannot choose the best temperature. We can only choose the best material. And finally, we are ready to draw our conclusions. At minus 10 degrees, there is no difference among the materials. At 20 degrees, materials 2 and 3 present longer battery life than material 1. And at 50 degrees, also there is no difference among the materials. Our final conclusion: materials 2 and 3 present the same behavior, and the choice between them can be performed based on other characteristics, such as cost.